Clap. So today we are going to solve an exciting tree problem from the Leetcode, that is 3068 problem number from the Leetcode, and this is in the today contest question. This question is hard mark and question having a saying that find the maximum sum of nodes, right? Let's read the statement, given problem statement, and we'll then go through. Okay, so let me expand this, and so we'll go through the statement clearly. Okay, so the question is saying that there exists an undirected nodes with n nodes, that is number from 0 to n minus 1, right? Means let's suppose if their nodes is given 5 number of nodes are given, right? So your nodes will start from 0 to 4. So you have given a 0 index to the array integers, right? And that is called array as of length n minus 1. So if n we have given, right, number of nodes we have given, so as will become what? Let's suppose number of nodes is 5, and how many edges will be there? Means 4 edges will be there, right? So the edges having the length 4, where each edge contains u and v, right? Means u and v are two nodes that connects each other, right? So let's see this further. So that indicates that there is an edge between node u and v in the tree. You are also given a positive integer k, right? And 0 indexed array of non-negative integer nums of length n. Means nums at I represent the value of the node number I. Means the element that we have given in the nums is the value of the node that is numbered as I, as index. Further statement saying that Alice wants the sum or value of tree nodes to be maximum for which Alice can perform the following operations any number of times, including 0 on the tree. What is the operation? Choose any u and v, any as you choose, and connecting the nodes u and v that update their values as nums at u and nums at v can be joined by k, and it will update their value. We have to return the maximum possible value, maximum possible sum of values Alice can achieve by performing any number of times, any number of operations he can perform, right? So we have to return that. Okay, so if you see that this is the nums we have given 1 2 1, and k we have given it 3, as we have given like this. Okay, means nums we have given, these are the elements 1 2 1, means these are the value of the nodes. So what are the nodes is 0 1 2, means we have given, let's suppose 1 2 1, means 1 is the value of node at 0. Node at 1 having the value is 2. Node at 2 is what? Value is 1. And the k we have given as is 0 and 1. So node 0 and 1 connecting this node, this is and 0 2. So there is 2 s, this one and this one. So you can see in the s's, right? Now Alice can achieve the maximum sum of 6 using a single operations. So let's choose the as 0 2. So nums at 0 and nums at 2, right? If you'll take, right, nums at 0 nums and 2, means we are taking the first edge, right? So what is the value? Nums at 0 having 1 and nums at 2 value having 2, right? So if you'll do the JOR, right, so nums at 0 is 1 and JOR value is 3, k value is 3, then we'll do 1 JOR 3 and you will get 2, and the array nums becomes what? 1 to 1, and it will become 2 to 2. If you do the sum, right, 2 plus 2 plus 2 becomes 6, right? And it can be shown 6 is the maximum achievable sum of values, right? And you will return the 6. I hope you understand, right? So in this way we have to find the maximum sum of you can say these operations, right? After performing these operations, and you have to return the maximum possible sum of the values that they can achieve. Similarly, the other examples we have, let's suppose nums we have 2 and 3, the value we have given at 0 is 2 and 3. Okay, so these s we have given. So if we'll take the s first, if we'll choose the s first, you will see that this is 2, right? And if we'll take the JOR 7, k value is 7, you will see this is coming 5, right? So nums at 1 becomes what? This is the nums at 0, and nums at 1 becomes what? 3 JOR 7 is 4. If you see the sum array nums becomes 2 3, right? And it is now becomes what? 5 4, right? So for the first value of the nums is previously was 2, now it become 5, and second value was 3, it become 4. If you do the sum, it will get 9. It means 9 is the maximum achievable sum of values. Now further understand this example. So in the third example, we have nums we have given like this, and k we have given 3, and these are the edges we have given. So if you perform all these operations, right, similarly that we have performed here, you will see that you will get 42, and that we have to perform, right? So it is saying maximum achievable sum is 42, which can be achieved by allies performing no operations. It means what? We have to, if there is no operations can be performed, right, you will get 7 7 7 7 7 like this. If you do all the 7, so I think 7 is 6 times 7 into 6 is 42, so total sum is coming 14. If there is no operations, just do the sum and return it. Okay, so in this case you have to understand, if we can do, we can take the XOR, right, we can perform the operations, then you will get the updated value at these nums, and you have to return the answer. If you are not able to perform the operations, you will return directly, you will do the sum, and you will think that you have the question now for the example 3. So why you have taken these two examples, the XOR operations, right, but you have not taken the XOR operations on the third one? Is the question coming to your mind or not? Right? Means, why some examples not performing the operations, and directly we are doing sum and we are returning the answer? So why ls not performing any operations here? Is the question coming to you or not? If it is coming to you, that is a great question, right? Yes, allies cannot perform these operations because it is absolutely possible that the optimal solutions that we are going to perform in this case will have no operations at all. What I'm saying means optimal solutions, right? If you want the optimal solution to get, right, means optimal maximum achievable, you can say, right? If you want to achieve the maximum sum, right, in that case, there we can take no operations and will return. Why? Let's suppose, don't think that this forms a star shaped tree, and and so that it is making it is not giving the uh, correct answer, right? Okay, or if this making a star shape, right, in this case will not do any operations, right? Okay, so if this forms a star shaped tree, right, but again remember, the tree structure doesn't matter for the sum. We only care about the gains from applying the XOR, right? If you observe that when we are making the XOR over these two, right, what is coming? 5 is coming. When we are operating on this XOR, what is coming? 4 is coming. Means this 5 is more than this 2. This 4 is more than this 3. Means it's good, right? We can achieve maximum sum. In that case, we will perform the XOR, right, on each element, on each edges, each node, right? So each node that we have given, right, let's suppose for edges, if any edge we are going to choose, right, we will perform this XOR operation only if the resulting value is more than this previous value. Otherwise, we will not do any operations, and we'll do sum of the nums and we return it. As you can see here, right, we have 0 1 and 0 2, both two things we have given, right? So when we are taking the first is, let's suppose 0 1, right, it was what? 0 0 1, let's suppose first we choose the edge 0 2. Okay, so nums at 0, and nums at 2, how it becomes? So first we have taken 1 XOR 3, so 1 is less than 2, and so we'll say, yeah, we can make the performance. Okay, but when we are talking about what? Other values, right, the 2, we have not taken anything, right? 0 1 we have not taken. Why we have not taken 0 1? That is not required. But if you take 1 and 2, yes, only one operations will do, single operation will do, and will update it. Similarly, we only care about the gains from applying the XOR. So in this case, let's suppose if we'll take the gains, right, of any of these numbers. So 3 is maximum value, 7 is maximum value, and 3 is smaller value, right? So if you perform, let's suppose 7 XOR 3, 7 XOR 3, if we'll do, what will come? 4 will come. What will come? 4 will come. So here, what we have to write? What is the gain here? 4 minus 7. It become what? Minus 3. So we have to write here minus 3. And similarly, we have to write for all these values. All these values become what? Minus 3, minus 3, minus 3. It means all become negative. So if all will become negative, right? Should we perform any operations? No, right? Since all gains are negative. So after applying the XOR operation, it will reduce the total sum. And we only apply XOR operation when the net gains is possible, right? So the final decision is that do nothing and leave sum. In this case, leave the sum, right, as it is to maximize the total sum. If you will not do, you will get all the values in the minus 3, minus 3, minus 3 like this. How many times? 6 times, because 6 elements here, and then the negative value will come. But if you leave, if you will not apply any operations, if you will not do anything, you will get 42. So the best answer is 42. In this case, do not do any operations. I hope you understand, guys, right? So what is the takeaway here? You perform XOR operations only if they increase the total sum. If no has a if no node has a positive gain, right, the best moves is not perform any operations at all. It means you perform XOR operations only if they increase the total sum, right? If no node has a positive gain, right, the best move is to not perform any operations at all. I hope you understand, right? What we have given, we have three nodes, we have given n nodes, we have given, it means this is a connected but no cycle is there. Okay, if n nodes we have given here in this tree, means this is connected, all the nodes are connected with each other, but there is no cycle is there. So each node has value nums at I, right? If we want to see the nodes value, we can see at nums at I, and we can repeatedly pick any as u and v, right? And you can update nums at u, nums at v, means the previous given value we can update to maximize the total sum of all those nums, right? But you have to make you have to take a XOR of these operations, right? If the XOR gives you larger value, you update it, otherwise leave that things. And then our goal is to maximize the total sum of all the nums at I, right? So what is the intuition? So the intuition behind this problem is you have to make how the XOR operations on this edge can affect the overall sum of the nodes value in a tree, and that then we have to understand how statistically you can apply the operations, right? So what is the key observations? So key observations, you can do the XORing is a pairwise. So each operations will do the XOR. Two nodes will be there at once. We cannot XOR a single node unless it is connected to another, right? If any edge you are picking, you have to do the XORing both nodes. The XOR is reversible. Doing this operation twice on the same edge brings the numbers back to the originals, right? So if you'll do any XOR, right, you have to apply back to the same node, right? So if you apply, let's suppose in this example, let's suppose if you do the reversible, right, if you do the operation 2 times, right, what will happen? You will get the same value again. The previous value you will get again. That you know, I think, right? What does XOR do? XOR operations changes the bit of a number. When a XOR number nums with the k, result nums XOR k might be What is the larger than the nums? If the positive gains happens, if negative gain happens, means smaller than the nums, that we have seen already. Okay, so what is the critical insights? We only want to apply JOR on the nodes where it increases the value, but since we do it in the pair edges, we can only JOR an even number of nodes that we have been given in the edge, or you can say pair. So this leads to, if the number of nodes with the positive gain is there, we'll apply the JOR all of them. If the number is odd, remove the one with the smallest gain and list, you can say, or list negative impact, right? Or JOR is the rest. What is the strategies here? We will calculate the gains at I. How? You can take the nums at I, you can make the JOR, and you will do minus nums at I. Okay. So this formula will give you the gains at I, right? Now we have to track the total original sum of positive gains, count the positive gains, and the smallest gain to potentially drop if the count is odd. If the count is even, add all gains. If the count is odd, drop the smallest gain to make the count even. Okay, means first of all, we'll do the gain. You will calculate the gain. Then you have to find the total original sum, then the sum of positive gains and the positive gains count, and you have to drop the smallest gain, right? Like this we will go and we'll do. Okay, so for example, let's suppose we have given 5 to 1 case 3. If do the joining, if you say that we are getting the gains plus 1, we are getting 5 jor 3, it means 6 minus this 5 minus 6 minus 5 will come plus 1. Similarly, if you do the JOR here, we are getting 1, right? The previous value is 2, so you will get minus 1 gain. Similarly, we will get the gain plus 1 because it was 1. It means, you see, we are getting the gains here, right? And the nodes with the positive gains become what? 5 and 1, right? So 5 and 1 having the total gains is plus 1 will get the 2, and so the count is how many? 2. So this is even. Let's understand, if we have nodes with the positive gains, right? Let's suppose the 5 and 1 we have got the gain 2, right? That is a count is 2, means this is an even, right? So what we will do, we'll apply the JOR to the both and the sum increases, right? If you had an odd count, let's say 3 positive gains in the node, so you will drop the least gainful one to mark the JOR and JOR it nodes even, right? Why the even counts? Because you can only JOR pair of nodes and the total number of affected nodes must be even. This constant drives the entire solution. Okay, I think you have understood, right? Means, let's suppose we are talking about this one. If you try to operate on these, right? So how many counts we have got on these two counts? So it is saying that we will apply the JOR to the both and the sum will increases, right? If you had an odd count, right? Let's suppose the 3, right? So the positive gain nodes will be there, 3, let's say 3 positive gains nodes will be there, right? So you have to drop at least the gainful one to make the number JOR nodes even. One of them you have to drop. Why the even counts? Because you can only JOR the pair of nodes. The total number of affected nodes must be even. This constant drives the entire solution. Okay, and so we can say the approach will be, we'll apply the JOR gain, right? We'll calculate the JOR gain. How? Using this formula, gains at I, will nums at I, will take the JOR and will do minus nums at I, and for each node you will compute the gain. How? At this. So this is the change in the value if you apply the JOR operation. So the calculated value will do minus, then you will get the gains. So the select, we'll do the select positive gains, and for that we'll only consider gains at I should be greater than 0, and since we apply the JOR operations, right, then we'll select the gains only. If gains at I is greater than 0, then we'll apply the JOR right value. Further, we'll ensure the even count, since the JOR must be applied to both nodes of the edges, right? So the number of nodes must be even, that we have already seen. If the count is odd, remove the smallest gain from them, right, and make it even. So the total answer will come out. Total sum will come what? Sum at nums, or all the sums, right, and the selected gains. Okay, So the algorithm will become what? We have to initialize this sum. So we'll initialize the total sum from where? Sum of nums. We'll take the sum of nums of all the elements. And for each I, we'll calculate the gains, right? If the gain is greater than 0, we'll add in the gain list. If the gain list is size is odd, we'll remove the smallest gain and we'll add all the gains in the gain list to the total sum. And finally, we'll return the total sum. You pause this video, try by yourself. Okay, let's go to the Leetcode and understand the codes by step by step. The first of all, we'll initialize total sum, positive gains, and the main gains, right? So as we have given the nums, k, and ages we have given, so we will in the first step we will do what? We'll initialize the total sum, positive gain count, and the main gain loss. So these are the variables we'll initialize, like total gain is equal to 0, positive gain count is 0, and the main gain loss will take the you can say integer max value, infinite value will take, and we'll have the main gain loss. Okay, we'll iterate over the all the nodes and we'll calculate the gains. How? We will take this loop array of loops, right? And you will get what? All elements you will iterate one by one, right? So let's iterate the elements of the nums and you will find the job value. So you will find the job value, you will do the minus with the nums, you will get the gain, right? Now this gain, you have to keep this gain, right? If this gain is greater than 0, we'll do some operations, but before that you have to also add the we have to iterate, we are iterating this, right? And we have to also count the total sum, right? Because total sum we required, right? So if the gain is positive, right, it's a candidate for the JOR. It means we have to update, we have to add into the JOR, right? If this is a positive gain count plus, we have to track the number of gainful nodes, how many gainful nodes we have to here. So positive gain count means the nodes we have to take, means from where we are getting the gain, and we'll take we'll make the minimum, which one is minimum, right? Either you will get the minimum gain loss and the gain. So we'll take the absolute value and we'll take which one is minimum, that will store the mean gain. Okay, so we'll keep track the minimum absolute gain that is used if we need to skip one or not. Okay, and finally we'll check if the count gainful nodes is odd, we'll drop the smallest one, right? How? We'll do minus. So you have the smallest one, right, already here, and then you will do minus with the total sum, and finally you will return the total sum because this is your optimized value, right? So let's have given and k we have given. So if you find the gains, right, you can find the gains like this for each element, and you can observe that we have nodes 0, 2 and 3, 0, 2, 0, 2 and 3, this one. Okay, here we are getting 6 positive, here we are getting positive, here we are getting positive. Okay, so all these are positive counts as you can see here. So these are the nodes, right, and we have the positive counts. Since it's odd, right, we are getting the 3 nodes, right? So this is odd, so we drop the smallest gain from the these 3. So which one is the smallest one, that we will see. Let's suppose we will get these, all we are getting what gain is 6, right? 6, 6, 6 we are getting. So we'll take one of these, we will drop. Let's suppose we'll drop the 6. Now the total gain is 6 plus 6, because all are getting, here we are also getting 6, here we are also getting 6, here we are also getting 6. Either which one is the smallest one? No one is the smallest one. So we'll keep one of 2 will keep, and one of 1 will drop it, right? So we'll drop the 1 and then we'll get what? 12. So we'll do the total sum, right? We'll get the total sum as you know. So we'll get 24. The total is, how we'll get the total? This is the original total sum, right? So how we'll get the total? Means the original sum and will the total gain applied, we will get 256, but we must deduct a smallest gain. So from the 256 we have to do minus 6, you will get 260, and that will be our answer. Okay, so let's recap it so you'll understand. I think you have understood, so let's recap it. Okay, so first of all, we'll use the JOR only when it increases the value. We'll keep track of the gain from joring, and JOR in the pair we will do, not in the single, right? We'll do the in the pair. So when we are doing the JOR, we'll do in the pairs. So only even number of gain gainful nodes can be joined, right? And we'll drop the smallest gain if the count is odd, right? So this is a very beautiful example of combining the greedy strategy with the bit manipulation in the tree. I hope you understand this video, guys, and let me know in the comment section that you have understood this problem, right? And if you found this video useful, give it a like, subscribe, and comment your questions or suggestions below. And happy coding. See you in the next one, guys.